Hmm. Now, yesterday we studied about the natural convection. In natural convection, you know what is a laminar flow and turbulent flow, and how to care what the relation between the Nusselt number and the Grashof number, and these are dimensionless numbers we studied. And we'll go for this one. Just see, I will tell you these are the again basic concepts in convection. There's something called convection boundary layers. Okay, usually these will be explained in natural convection as well as a forced convection, but only try to understand what are these profiles and how these are categorized in done what is this. Now it's very important, like velocity boundary layers. What are those? Got it. Uh, just see this graph. Now base, this is x-axis and this is y-axis. Now if you consider any one plate or a surface, that is considered to be x-axis. Got it. Now any air or a hot fluid is flowing above this one. At that time, this is a velocity of that wind we can see, or air which is flowing on that surface. Or you can take x as this much, as you can take a thick plate, what you can see. You can take this one as a thick plate, and on which hot fluid or a hot air is flowing. At that time, what will happen? Now just see, this is, I have drawn a profile in the sense what this is a nature of fluid or air which is flowing above the plate, how these characteristics is going to possess. Now this is called a velocity boundary layer, which one up to this maximum point, and this is velocity profile. Got it. Now if you see this graph, what it shows, what will you going to understand, it is a parabolic like this. It is slightly, it is zero at the exactly in starting point of the plate, and gradually increasing, and it take a sharp curve and almost maximum at the uh, how much height of fluid, or you can see what is the thickness of the fluid above this plate. In the sense what, the air or a fluid which is in contact with the plate, it is going to resist, it have going to have some resistance with respect to the surface of the plate. That's why the velocity is very less. When another fluid layer, adjacent layer, will come slightly above, the velocity is increased as compared to the layer which is nearer to the plate. And similarly, another adjacent layer which is much higher than the height of the plate, here in, the velocity is slightly increasing. And if you go on doing it, if you move away from the plate, the velocity is maximum, and at the height it is maximum velocity you are going to get it. This is how the velocity of the air or a fluid above the plate is getting distributed. Got it. That's why it is called a velocity profile. Now we are going to call this one as a velocity boundary layer. Okay. Now this is velocity boundary layer. In velocity boundary layer, what you are going to study, anything. If this is your plate, a fluid or a hot fluid or air which is flowing above this surface, this is the characteristic qualities of that fluid or air which is going to flow above the plate. Now this delta, we are taken a maximum height of that fluid or air. Hmm. Now that's called a velocity boundary layer on a flat plate we have taken, and this, in this case, the plate is horizontal. Sometimes we may take a vertical plate also. Got it. And you may see that, so where these examples will come into the picture, whenever when you see horizontal, these kind of horizontal plates, usually you're going to experience in case of where uh, on which, like in oven, on which a base part is very much hot there. And in case of vertical plate, when you take the vertical plate in this direction, sometimes if you take a vertical plate in this direction, at that time you are going to get a vertical, like in case of hot tubes. Got it. A vertical tubes. In such cases, a vertical, our specimen or our body or system is in vertical condition, at that time it is going to lose the heat to the environment. At that time again velocity profile is slightly different. But here we have considered a horizontal surface. On that surface we are going to study this velocity profile. Now similarly, if I go what this it says, the just a slight theory I have written behind this one. A region of the flow over the surface bounded by delta. In the sense what, this is nothing but a thickness, hmm? thickness of the flow, in which effects of a viscous shearing forces caused by fluid viscosity are observed is called a velocity boundary layer or hydrodynamic boundary layer. Both are same. If you see these keywords, just see on the surface with the effects of viscosity sharing. Got it? Viscosity sharing forces will come into the picture and viscosity. Understood? These two parameters are going to contribute greatly to have for velocity profile, viscous sharing as well as fluid viscosity. Because you know what is viscosity? Viscosity is the resistance upward to the fluid layers, adjacent fluid layers. Got it? That is called a viscosity here. But in this case, viscosity sharing forces will come into the picture. Got it? Caused by the fluid viscosity, adjacent fluid layers. That is called velocity boundary layer or hydrodynamic boundary layer. Now, let us see. We'll go further. The thickness of boundary layer delta is generally defined as distance from surface at which local viscosity, local velocity u is equal to 0.99 for free stream velocity u infinity. What is the meaning of this statement? What is there? See, local velocity u is equal to 0.99 for free stream velocity u infinity. If I go here, that the meaning is here, this region. In the sense what? You have taken u is equal to 0.99. In the sense what? Nearly equal to 1. When you say velocity is 1, the velocity is maximum. And that velocity is equal to nothing but which is flowing. This is a free stream. That's why we are given u infinity. In the sense what? If any air is flowing over here, having a normal air velocity is maximum velocity is this much, but that maximum velocity will come when in this is at peak. That is called a free layer here. And here the layer on which it will come here, this layer which is in contact with the plate has got less velocity. That's why u is equal to 0.99, in the sense what? Almost equal to the velocity of natural air. Understood? That is what explained here. Hmm? Understood? Defined as, see, distance from the surface at which local velocity u is equal to 0.99 of free stream velocity u infinity, or you can say uf also, environment whatever, or u naught also you can take, just they are given a suffix infinity. Hmm? This is all about velocity. We studied with respect to the velocity. Okay, whether it is a hot fluid or whether it is a cold fluid. In this case, the plate may be hot or the fluid may be cold, or the plate may be at normal temperature, or here the hot waves may be flowing here. Any either case, but only thing that we are concentrated only on velocity. Got it? Not on thermal background, in the sense what? Temperatures. Now this is only with respect to velocity. Then let's see, we'll move further. And now what we will do, now we will discuss about thermal, okay, boundary layer. In the sense what? Here in thermal boundary layer, what will happen? The temperature, we need to study the variation of temperature with respect to the plate, horizontal plate, when any fluid or any air is passing above this one. Consider a fluid at a temperature T infinity flows over a surface at a constant temperature Ts. In the sense what? This is a surface temperature Ts. The fluid particles in adjacent layer to the plate get the same temperature that of the surface. The particles exchange heat energy with particles in adjoining the fluid layer, and so on. As a result, the temperature gradient are developed in the fluid layers, and temperature profile is developed in the fluid flow, which ranges from surface temperature Ts at the surface to the fluid temperature T infinity, sufficiently for from the surface in y direction in the exactly vertically upward. In the sense what? How much of depth of air or thickness, or you can say head. The flow region over a surface in which temperature variation in the direction normal to the surface is observed is called a thermal boundary layer. What you written over here, I will show you in case of diagram. Just see here. These two, consider these two cases now. Okay. Now just I will say these two cases. Hmm. Now if you look at all these two, now just only concentrate on this much. Only this much you take it. Now see this one. What the graph is there? What is the natural velocity? This is Ts surface. Okay. This is a plate. Okay, horizontal plate. This is Ts. Hmm? And that's why here cold fluid or hot plate. In this case, what is happening? The plate is hot, but air is at normal temperature, or it is at cool air is passing. Hmm? Now, what will happen when the any air is going to pass? The temperature profile is exactly opposite as that of velocity. Correct? Why? You know, it's a very basic fundamental thing. Got it? Why? Because above this, the air which is come in contact with the hot surface, there the temperature or the exchange of energy is maximum, because that adjacent layer of the air will come in contact with hot plate, and when any air which will come in contact with a hot plate, there will be a energy exchange at the greater extent. And if you go consider another adjacent layer above that, it is less exposed to the hot plate, that's why energy exchange is less. Understood? That's why here the temperature profile is go on decreasing and it comes to the normal temperature when at the maximum height. This at what we are going to call this temperature, this peak temperature is same equal to the T infinity when open. This is at the open surface here maximum. When you come below at the depth of the air, when you come to nearer to the plate, the thermal exchange, energy exchange is more. Why? Because it is in contact with this. Now, this is one case what you have studied. In this case, what you have taken here, our horizontal plate is hot and air is cool. This is what thermal boundary layer, and this is what temperature profile. In both I have shown, and this region and this region both I have shown. Got it? Hmm. This is temperature profile. When the plate is hot, air is cool. Now come to this point. Let us see. Now see here. Here in this case also the same thing, but only thing that here hot air is flowing on a cold plate. Here our plate is cool, but air which is passing above this one is as what? Hot air. Understood? And this time what this temperature profile and velocity profile almost both are same, almost same. Correct? Why? Why it is so? Why? Because now just imagine air is flowing like this. Hmm? Air is flowing. The air is hot, but the plate is cool. Hmm? Now, what will happen? The maximum temperature you are going to experience away from the plate, not with respect to the plate. Correct? Why? Any hot air will come in contact with the surface of the plate, it is going to lose a energy. Got it? In the sense what? The temperature is less when you come nearer to the plate, but when you go away from the plate, the temperature is more. Got it? That's why here this shows these directions of the lines will show you the temperature profile. In the sense what? The maximum temperature you are going to experience when you come away from the plate, and when you come nearer to the plate, the temperature is go on decreasing. Why? Because the plate is going to absorb a temperature of the air. At that time when the plate is going to absorb the temperature of the air is going to lose amount of energy. At that time the temperature is less. Got it? That's why the temperature profile is gradually decreasing when you come nearer and nearer to the plate. Understood? But in this case exactly opposite. Why? Because the plate is hot and the air is cool. But exactly here changed. The plate is cold plate and hot fluid on a cold plate. These two are a different same, but only thing that the body is changed. In the sense what? The hot body is changed. We have taken this one as a hot plate and hot fluid. The fluid maybe it may be a water, it may be a air, it may be a gas, whatever. Understood? Now that's why if you study this temperature profile, then you will get to know how energy exchange will going to take place with respect to two bodies. Got it? Now this is, now keep it in mind, it's very simple. You need to analyze when, how any fluid or a air which is going to come in contact with the body which is cooler or hotter, their energy exchange will going to takes place. And where is the maximum energy exchange will be there? Though there the temperature profile is increased, that much you need to take care. Understood? Now here the plate, in this case the plate is hot and air is cool. Wherever the hot surface is there, that's why you're going to get a more temperature. And wherever the here, if you go away from the plate, the adjacent layer of the air is there, that's why energy exchange is less. But in this case what will happen? The air, this much part is hot, above part is hot, and the below part is cool. That's why if you go here and above, here one layer, here one layer, those are almost hot and the maximum temperature. When you come below and you are going to come in contact with this cool plate, that's why the temperature is less. Hmm? Now this is with respect to the thermal boundary layer. Hmm? What we studied is thermal boundary layer. Here what we studied is velocity boundary layer. Understood? I hope these concepts you studied in, uh, but only velocity boundary, how the velocity is going to change in a flow, you studied in fluid mechanics. Got it? In a flow of a pipe or a flow over a plate, buoyancy effect, all you studied in fluid mechanics. Same thing over here, but we are categorized into velocity as well as a temperature. We are going to study as a different parameters. These two are different parameters. Now, these are called in convection boundary layers. Now, usually these kind of concepts will be studied in forced convection as well as a natural convection, because these are very much important. Because here in convection, ultimate goal is to find out is convective heat transfer coefficient. That's why this convective heat transfer coefficient again depends upon what? Greatly depends upon velocity as well as temperature. That's why we are going to study these two. And if you go back to your Reynolds number and Nusselt number, again the temperature as well as velocity will come into the picture. Okay, the temperature again, what is that? Thermal conductivity. Okay, and beta will come in Grashof number, that is thermal expansion coefficient. Correct? That's why these two parameters we need to study. Hmm. Now let's see, we'll move further. I hope you understood these two concepts, velocity boundary layer and thermal boundary layer. Now let us see, by using these one, what best we can solve some problems, how, what kind of a problems may come. Okay, now let us see, go through this simple problem. Water flows at 20 degrees Celsius at 8 kg per second. In the sense what, this is what a mass flow rate of water, and this is a water temperature is 20 degrees Celsius. Water flows at 20 degrees Celsius at 8 kg per second through the diffuser having 3 centimeter diameter at the entrance and 0.07 centimeter at the diameter at the exit. Calculate fluid velocity and Reynolds number at the inlet and the exit of the diffuser. Very simple problem. A section of a pipe they have taken. Diffuser is nothing but a section of a pipe wherein it has got a different diameters at the inlet and the exit. And by this definition, of the problem, if you see, at the entrance the diameter is less, at the exit the diameter is more, 3 centimeter and 7 centimeter what they are given. Okay. Hmm. now if you see what the, this is a given diameter, sorry, here it is not 0.7, it is a 7 centimeter. Okay, it is 7, not 0.7. At the exit, now if I show you the diffuser, this is what is a diffuser. I have taken a section of a pipe from here to here, this is inlet and this is outlet. Hmm? At the inlet This is nothing but a flow from here. Flow rate is 8 kg per second at the inlet. At the outlet, the diameter is bigger. At the inlet, the diameter is less. What they told you to calculate in this? Velocity as well as Reynolds number. Correct? Let us see how we can approach this problem. We need to calculate velocity at inlet, velocity at outlet, Reynolds number at inlet, Reynolds number at outlet. These two we need to calculate. For that, just I will tell you, go back to your fluid mechanics. There, something you have written called continuity equation. Correct? Continuity equation in a pipe or a channel. What is that? U1 V1 you used to write it, correct? Is equal to U2 V2. The same concept if you apply over here. Now, these two I have written. What? Velocity at the inlet and outlet. These are the two parameters we need to calculate. Reynolds number at the inlet and exit of the diffuser we need to calculate. To calculate these two, what I am going to do, I am making assumption that steady flow condition. In the sense, there is no any change in the flow condition. We need to assume this. By assuming this, what we will do, from your data handbook, we can calculate the parameters associated with water at 20 degrees Celsius. If you open there, the in table, the water or fluid at 20 degrees Celsius, the density is 1000 kg per meter cube, and kinematic viscosity, this is mu 1007.4 into 10 raised to minus 8 kg meter per meter second, kg per meter second. Now these two, this much of parameters I am going to take from your data handbook. When the table is there, if you go properties of the fluid, the title of the table, if you go there, and the water they are given there, if you go and if you see the parameters, water at 20 degrees Celsius, the kinematic viscosity and density is given this one. Next, now what we need to do, just I will calculate the area. What is cross sectional area? Somewhere at this region, area inlet, and this is at outlet. These two we will see. Let us see now. Now calculate the area. What is this? Pi by 4 d square. At inlet I have taken d1, at outlet I have taken d2. Pi by 4 d1 square is equal to what? Pi by 4 d. Convert this one in terms of meter, that is 3 centimeter. I convert this one in meter, 0.03, and area at the inlet is 7.067 into 10 raised to minus 4 meter square. Next, similarly, if I calculate area at the exit is pi by 4 d square. This d is nothing but exit diameter. How much? 7 centimeter they are given. I convert it into a meter and it leads to an answer of 3.484 into 10 raised to minus 3 meter square. Of course, this area is more bigger as compared to the A1. Yes, because the diameter is more. Now just see here, it is minus 3 and it is here minus 4. This quantity is more bigger as compared to the this one. Now moving on to the next. I told you, no? We are going to make use of continuity equation. Using the continuity equation at the inlet and outlet, what we can write? Inlet velocity at the inlet is nothing but mass flow rate divided by density into the area. This is nothing but a velocity at the inlet. Mass we know, they are given how much? 8 kg per second. They are given a density we calculated from the data handbook, area we calculated. Correct? Substitute all these values and velocity at the inlet is 11.32 meter per second. This is a velocity at the inlet. Similarly, if I go for exit U2, it is same mass flow rate divided by density into the area. Here again 8 kg per second, density is 1000, area is this much at the exit. At that time I am going to get the velocity is 2.08 meter per second. It is less as compared to the inlet. Okay, outlet, the velocity is less. Now if you, according to the problem, they told you to calculate velocity at the inlet and outlet, we calculated. Now we need to calculate the second parameter, the Reynolds number at the inlet and exit. We need to calculate. Okay, what is that Reynolds number at the inlet? The respective Reynolds number at the inlet is RE1. I have taken 1 at the inlet. Reynolds number suffix I have given RE and 1. It is rho velocity diameter divided by kinematic viscosity. Correct. Now just see the Reynolds number greatly depends upon this velocity. Got it? That's why I have written by a different color called red. See, density will be here and what the diameter kinematic viscosity, but greater depends this directly proportional to the what velocity and density. Correct. That's why I have written by here different color with velocity. As the change in velocity, Reynolds number, just look at it with these two parameters. Now, if I calculate the Reynolds number at the inlet, it comes out by substituting all the values, it comes about 3,37,105 when the velocity is maximum. Similarly, if I go for the Reynolds number at the exit, de- density, velocity at the exit, diameter divided by kinematic viscosity, and here the velocity is 2.08 and here velocity is 11.32. And if I calculate at the exit, the velocity or with respect to the Reynolds number will comes about 1,44,530. But wherein at the inlet, 3,37,105. The huge difference between these two. Got it? In the sense what again? I hope now you studied why you studied about the velocity profile. Got it? That's why the Reynolds number at the inlet is this, Reynolds number at the exit is this much. This is what in the problem they told you to calculate. See, I have written these two. Velocity of water at the inlet and the exit of the diffuser, Reynolds number at the inlet and exit of the diffuser. Understood? A very simple problem, but now you experiencing how these concepts are applied somewhere in real life. Now just see, that's why again this is a dimensional number. As the number is more, you can say that at that time velocity is more. Whenever the number is this, the velocity is less. That's why the Reynolds number is having a small value, here a bigger value. Again, depends upon these ranges only what we are going to multiply with another dimensional parameter, that is Grashof number. And you, when you multiply these two, you are going to multiply and you are going to decide the Nusselt number. Yesterday's class we solved one problem. Similar way, here also it greatly depends upon velocity. Okay, I hope you understood today's class. Got it? That's why I solved a very simple problem. I explained only the two concepts and those how you're going to make use of just I shown here. Now in next class, what we will do, we will take another examples with the different concepts and more examples we will solve on this. I hope almost we are in the end of the syllabus. If I complete thoroughly natural convection, forced convection both and solve the problem, everything is got finished. Understood? It's very easy. If you have got any problem regarding to the today's class, just tell me. Hardly 1 minute is there, or just you message me so that we will reply you back. Hello, hello. Anybody like Srinath, Vikas, Pratibha is also here. Huh? I
No
hope
doubt.
today's class is clear, no?
Yes, sir.
Hello. The similar problems will come in the final examination also, and just you should know how to apply these problems, concepts, what you studied in solving the problem. You should know Reynolds number. Even examination, if you're not able to remember the Reynolds number, also here there in data handbook everything is available. But you should know how to retract the data from the data handbook and how to make use in solving these problems. Okay. If any problem with regarding to the today's class, just message class. I will sort it out, and we'll go for the next topic. Okay. Okay. Thank you.